Hi everyone! Today I'm going to show you how a light guide works. Also, I will explain the basic principles of light propagation through a light guide, and in the end you will be able to use this knowledge to build your own light guide lamp. For example, a lamp that consists of several light fibers like the one that you can see here. Let's get into it. So what do we need for a light guide lamp? Of course, an LED. Then it helps to concentrate or collimate the light with a TIR lens. TIR stands for total internal reflection. We need this lens for efficient incoupling into the light guide. And of course, a light guiding material. Nearly every transparent or polished material is able to guide light. I used some low-cost parts that you can see here. Let's get familiar with some light guide basics. What you can see here is a light guide rod. It has a rectangular cross-section and the rod is made of PMMA or Plexiglass. The green rays that you see, they are coming from a light source that is located inside the material. The light source is emitting parallel rays. In the real world, we will never get these parallel light rays, but in this case, they help us to understand the effect of total internal reflection. Let's adjust the light direction to see what happens. The light gets reflected from the transition zone of PMMA and air. It gets reflected from the walls. This reflection is very efficient. It happens with nearly no loss. And on the other side of the light guide, the light is outcoupled. The direction of the emitted light is determined by the last reflection from the sidewall. Let's adjust the light direction of the light guide again. And if I increase the angle of incidence, light gets reflected just like before. The most important aspect of a light guide is the concept of the critical angle. When the incidence angle reaches this critical angle, light is not reflected from the sidewalls anymore. To calculate the critical angle, we need the refractive index of our light guiding material. Here we are using PMMA with a refractive index of 1.49. Also, we need the refractive index of air, which is 1. With these two values, we can calculate the critical angle. In our simulation, I've added two planes. The angle between these two planes represents the critical angle. That's the angle that we have just calculated. It's 42 degrees. As long as the incident angle is larger than the critical angle, light gets reflected by total internal reflection. In this case, the incidence angle is measured against the surface normal, or in other words, against the vertical plane that you can see here. But when the incidence angle gets smaller than the critical angle, light is exiting the light guide at the sidewalls. This is also an interesting case. Here the light gets reflected from the side walls, but also at the end of the light guide. At the end, the critical angle is not reached, so that light cannot exit. So the light is reflected back into the light guide. In other words, light is trapped and it cannot escape. Enough with the explanations. Let's build something.